Hello, here in this video we're going to look at 3.1, graphing quadratic functions. Here's the why. Quadratics are projectile motion. They are also used for business. So projectile motion, if you're not aware, is anytime we launch an object up through the air. And then we can ask questions such as how high or how far did something launch? So this is a lot of the sports, like with punting a football, shooting a basketball. Anytime an object leaves the ground and is flying through the air, it's modeled with a quadratic function. You can also use quadratics for other concepts such as maximizing profits or minimizing expenses by looking for either the top or the bottom of the U-shaped curve. So the concept of quadratic functions applies more broadly than just launching things. There's lots of situations that can be modeled with quadratics. So what we can think about here is, what's your favorite type of quadratic situation? Maybe you play a particular sport or have a certain type of hobby where you're launching something up through the air. Maybe you've done some type of business work where you look through and you're trying to maximize profits by charging money or making steps to making sure you're minimizing your profits. And what I mean by that in terms of maximizing profits would be, if I was just to make a quick sketch, the amount of money that you charge, so the price point that you set on something, ultimately impacts the profit that you make. To where if you're charging $0 for something, you're not making any profit. But also, if you charge $1 million or some large number that people aren't willing to pay for your product, you also make no money because no one buys it. And somewhere in the middle of those two is the point that you'd be looking for, to where, hey, this is the price that I should set, to where a lot of people still buy it, to where I'm not undercharging and making too little money. I'm not overcharging and making too little money like that way because not as many people buy it. But instead finding that price that you should set it to maximize profit. So along with quadratics comes new vocabulary, or applying old vocabulary, to a new concept here. Quadratic functions are going to have up to 3 pieces here. When you see that exponent of 2, that's going to let you know that that is the quadratic term. So in order for something to be a quadratic function, it must have an x squared as its highest exponent with x. So we must have a quadratic term. Now, you can still see other terms as well. You might see some linear terms in there, such as 2x or any coefficient with x. And then you'll also have the potential to see a constant. And that's just a regular old number. Together, these can make a quadratic function. Okay, so here are a couple diagrams of quadratic functions, and we're going to look at some of this vocabulary here. All right, so this shape right here, this arrow, it looks like it's kind of pointing at a y-intercept, because it is, but it's describing instead just the general U-shaped curve there. That's called a parabola. So you'll hear that term used often as we're discussing our quadratic functions. This next line is pointing to a dotted line that travels down through the middle of the quadratic, through the middle of the parabola, and it is the axis of symmetry. And if you look at it, you can understand why it would have that title. It's dividing the parabola into 2 halves, and it travels down through this bottom point, which can sometimes be at the top too, called a vertex. So the axis of symmetry will always pass through the vertex. The vertex is going to serve as essentially the center point of that parabola. Now, your vertex can be one of two types. It can be a maximum value, or if your quadratic opens up, it can be a minimum value. So a situation where we could use quadratics would be this right here, ticketing. The manager of a symphony computes that the symphony will earn negative 40p squared plus 1,100 p dollars per concert if they charge p dollars for tickets. What ticket price should the symphony charge in order to maximize its profits? That's going to be one that we just explore together in class. And then after we do 3.1, we're going to see how we can use data in our calculators to generate equations such as this. Because you might be confused on, well, where did he get all that from? How do you know, did these numbers fall from the sky? We'll see next section how we can use our calculators in statistics to come up with estimations about how things would go depending on what types of prices that we could set for our products. All right, so this section, as you saw, is called graphing quadratic functions. Quadratic functions have a little bit of complexity to them, definitely more than linear equations. Some of these steps that we're going to do can be done in various orders depending on the information that you've been given. But for the most part, here's what we're going to do to graph quadratics. I'm going to take us through this example. The first phase is to write the function in standard form. Now, what standard form is where we're going to go through and place the quadratic term first, the linear term second, and the constant term third. So standard form always has your quadratic term all the way to the left, your linear term second, and your constant term at the end. And then it says identify coefficients. These coefficients, the numbers that are with our x squared x and our constant, will be used for formulas as we graph quadratics. And it's a very simple ABC concept. So it's a very simple step of where A is going to be the coefficient with your quadratic term, B is your coefficient with your linear term, and C is just that constant term. So here's what we'll use them for. We just discussed on the previous page that the vertex is the center point of the quadratic. So that means the vertex is going to be very important for us to find. So what we're going to do is we are going to find the vertex. All right, and here's how we're going to do it. The vertex is a coordinate point. It's x comma y. To find the x-coordinate of our vertex, what we will do is use the formula negative b divided by 2a. So let's do that with our values here. We're going to find the x-coordinate of the vertex by doing the formula negative b divided by 2a. Our b value is 8. Our a value is 2. So that will tell us that we have a negative 8 over 4. The x-coordinate of our vertex is negative 2. Okay. However, that only tells us half of the information about our vertex. We need to now understand how we can find the y-coordinate. To find the y-coordinate, you're going to take what you got for x and you are going to evaluate. Essentially, we're going to plug in the x-coordinate into our function, and we're going to see what we get for our y-coordinate. So our function was 2x squared plus 8x plus 2. So I'm leaving a blank spot everywhere for my x. Let me erase this x here. And what we're going to plug into it is what we got for our x-coordinate. So we see our x-coordinate was -2. On this particular example, we are going to be substituting in -2. By order of operations, we'll do the exponent first. -2 squared is a +4. Here, 8 times -2 is a -16. And then we have a +2. So this value here is an 8. So we get 8 minus 16 plus 2. And if we add all those up, so 8 plus 2 is 10. 10 minus 16 is a -6. We now see here that our y-coordinate for our vertex is -6. Okay. We're going to do that process lots and lots of times over the course of this section even. So don't worry, we're going to find many, many vertexes. I'm going to go ahead and do what this box here that says, make a table and put the vertex in the center. I'm going to go ahead and place that there because the vertex is the center point of the quadratic, so we will need it there at the middle of our table. Now, when it says identify the y-intercept, the y-intercept is very easy to find. It's always 0, c. So for us, our y-intercept is 0, 2, because our c value was 2. As far as making the table is concerned, we'll just want to fill in some more values. I'm going to count down by 1, and I'll also count up by 1. So you can see in this box where it says graph the ordered pairs, check the axis of symmetry. The axis of symmetry is the dotted line that travels through the parabola, dividing it into 2 equal halves. And notice that on both sides of the axis of symmetry, that your y-coordinates are the same. So we can use that concept to speed up the table process. What that means is as long as we put the vertex in the middle, these 2 points are going to be the exact same as far as the y values are concerned. These 2 points are going to be the exact same as far as the y-coordinates are concerned. And so the way that helps us is that this 0 at the bottom of the table is our y-intercept. We can see our y-intercept was 0, 2. That means that this coordinate point also must be -4, 2. Let's go ahead and graph the points that we have so far, and kind of see what we're working with here. I'll start with the vertex first. It's at -2, -6. So all the way down here at the bottom of our page. Now, we've found 2 other points on it so far. We found 0, 2, and we found -4, 2. So you can already see that quadratic taking shape, but we'll need to find, the 2 more points that will land somewhere in this region here to help us kind of figure out the shape of our curve. So to do that, we will need to figure out one of these other values. Now, I do not need to find them both because they are going to be symmetrical around the axis of symmetry. So at this point, we can go to our function and we can choose either one of those to substitute in for x. I'm going to choose the -1 because it's smaller. And now we'll go through and evaluate. Negative 1 squared is 1. 8 times a negative 1 is a negative 8, plus a 2. And then here, this is a 2. So 2 minus 8 is negative 6. Negative 6 plus 2 is negative 4. So that means when I substitute in negative 1, I get a y value of negative 4, which also means that this one too is negative 4. And if you don't believe that, pause the video, substitute in negative 3, and you'll see that you get the exact same answer of negative 4. So we can come over here now and graph negative 1, negative 4, and negative 3, negative 4, to finish getting our U-shaped curve. So there was our very first graphing a quadratic. We'll do many more of these because, as you can see, there's various steps to it. It's much more complicated than linear equations, but the more we do these, the more we'll start to understand some of the special relationships between some of the different values that we'll see, and we'll ultimately become much faster and much more proficient at the process. As for the rest of this page, we will cover it together in class.